I highly recommend the steps that your book recommends for related rates problems. Sort of like the steps for the optimization problems, feel free to memorize them as steps or not. That it can work either way. But these are the things that you're going to need to do, and especially when you're first starting out, to have them sort of listed out for you so you remember each one can be helpful. Feel free to use this helpful tool. So we're going to try these steps on a couple of problems. Some things to note before we try it out. When I say write down the information that you have and the information you're looking for, in a related rates problem, almost all the time, except for like really trickily worded problems, you are looking for how fast or in what way some value is changing. They may or may not use the words with respect to time. So how fast is the something increasing, or at what rate is the something decreasing, or how is the something changing? These are your ideas. These are the times where you're going to have a related rates problem. The sketch, like I say in the note paper, a lot of these problems have a geometry aspect to them. The sketch is most helpful when you're trying to do step 3, which is to write an equation that relates all the variables that you're interested in. If you feel like you could write that equation easily without drawing a picture, feel free. We're going to differentiate, but once we have an equation, we'll differentiate with both sides with respect to time. And related rates is the place where we sometimes see that error that I've warned you about, which is you can't try to tell me f prime of 7 until you can write me an expression for f prime of x. So we have this idea in a related rates problem that something is changing. So we have the radius of a balloon is increasing, so as a result, the volume also increases. We might have some information. Remember when I froze that picture at the exact moment when the radius equaled 10 centimeters? I can do that, but I don't want to freeze anything, make something a constant, and then try to take the derivative, because the derivative of a constant is 0. So what I want to do is make sure that I still have all my variables intact before I try to, by intact I mean not replaced, still variables, not substituted in for. I want variables in my equation still before I take the derivative. After I've taken a derivative, now you can go ahead and make substitutions in. But this is a very common error, is just try to plug things in too early. So no plugging anything in. Anything that might have a chance of changing, no plugging in until after you've taken your derivative, and that's step 4. Typically at that point, you're going to be able to isolate that value that you're looking for, and you'll interpret your answer. A lot of times you will be asked to give units with your answer, and typically you'll get an extra point just for the units. So there's a point for the number part of your answer and a point for the units. You can keep your units with you all the way through a problem. It can get a little messy. I think you'll find with some reasoning you'd probably be able to put correct units on your answer at the end without. Or you can just keep it 2 separate problems that sort of run through one equation with units to get the units part, run through with the numbers to get the numbers part. We'll do some examples. So here we have a question started with spheres because we already have a memory of that formula for the volume of a sphere. A spherical balloon is inflated with helium at a rate of 100 pi cubic feet per minute. I have 2 separate questions. So question A, how fast is the balloon's radius increasing at the exact moment when the radius is 5 feet? So imagine balloon blowing up, blowing up, blowing up. We're going to acknowledge that it's going to keep growing, but try to, at one point, freeze the picture when the radius is 5 feet. So part 1, step 1, I know, whoops, that's not the marker. I know something about the rate at which the volume of the balloon is changing. They didn't use the word volume anywhere, right? But if you imagine, what does that mean that you're putting 100 pi cubic feet per minute of helium into the balloon? That's how the volume is changing. So the volume is increasing that much. So we know dV dt. Sometimes I write this out, so I may as well. We know dV dt, that's the rate of change of the volume with respect to time. I suggested you make a list of the things that you're looking for. We've been asked how fast is the radius increasing at some moment. So the thing we've been asked about is one specific value of dr dt. That's the rate at which the radius is changing with respect to time. How fast is the radius changing with respect to time? All right, so that was step 1. Step 2, draw a picture. So here we probably know already what equation we're going to write. I don't think that there's any confusion, but that's r. I have a sphere here. And the thing, what are some things that we know? I need to write an equation that relates, at the very least, v, because I know dv dt, and r, because I need dr dt. So I hope this is an obvious choice. I know already volume of a sphere, 4/3 pi r cubed. And it doesn't have to be any more complicated than that. There is this one equation that relates volume and radius with no other variables. So step 3 was to use my picture to help me write an equation, and it's got all the right stuff, but no derivatives, right? No derivatives in this equation. Now I'm going to take the derivative of both sides of this equation with respect to time. So this we've done already. dv dt is going to equal 4 pi r squared times dr dt. And now I'm going to look at question A. How fast is the balloon's radius increasing? So I want to know dr dt at the exact moment when the radius is 5 feet. So that tells me I can rewrite this equation. 4 pi times, let's see, I'm going to change color for things I know. I know that r, at this exact moment, it's okay to freeze the picture now because I've already taken the derivative. So I'm going to replace r with 5. I know dv dt is the rate at which the volume is changing. That's 100 pi. You know, I actually already went through and wrote out all these steps in the math type font. And I got excited and I started handwriting them in. So, but here's where I am, and then I'll switch over to what I've already done here. And the thing that I need to know, let's make that red so we don't lose it. My goal is to isolate this dr dt. So I'm going to try to solve that equation for dr dt. I know 100 pi is 4 times pi times 5 squared times dr dt. All right. So here's all that same stuff. So far, that was me taking the derivative of both sides of my original equation with respect to time. Now I know some of the things I'm going to replace. I see now here that I've written this all out with the units included. You can make a decision about whether you'd like to leave them in or leave them out and deal with them separately. So here's where I got 100 pi is equal to 100 pi. So that's the 4 pi times the 5 squared. 5 squared is 25, so 100 pi. So 100 pi cubic feet per minute is going to equal 100 pi square feet times whatever dr dt is. When I isolate dr dt, I get this final answer of 1 foot per minute. You have to stop and ask yourself. So I got those units by keeping all the units on all of my factors in this original equation. You might decide that that's not for you. To be honest, I don't usually do it like that. But I did, so let's double check. These units have to make sense, and they have to match this notation, so dr dt. So rate of change of radius with respect to time. So dr, that expression dr really means a tiny change in r divided by a tiny change in time. So what do you think the units on r are in this problem? Well, all our distances were measured in feet. So a tiny change in r should also be measured in feet. Time has been measured in minutes. So a tiny change in time should also be measured in minutes. And I get feet per minute as my units. That matches what I have. So final answer, 1 foot per minute. I have a second question. How fast is the surface area increasing at that instant? So let's just say, let's write this notation. I'm going to write it here so I remember. dr dt. And then I'm going to erase the slide and do this part B. And that was when r equaled 5 was 1 foot per minute. So notice DRDT, it changes. It was probably changing through the whole course of this problem. It's probably never the same for any two like moments in time in a row. So if I want to give a one number answer, I have to indicate where I've frozen DRDT. So I froze it at the time when the radius is 5. That's what this notation means. DRDT at the moment when r is 5 was equal to 1. So let me go back and answer this question. Okay, so knowing that my answer to question A, at the exact moment when the radius is 5 feet, the radius is changing at a rate of 1 foot per minute. Now I've been asked this follow-on question, how fast is the surface area increasing at that same moment? So to me that means the radius is 5 again. So I'm going to need an expression for surface area. Surface area of a cube is 4 pi r squared. Don't worry if you didn't know that. They will typically, they'll expect you to know volume of a sphere, volume of a cylinder. But other than that, I think you'll find that they'll be happy to give you formulas for important volumes that you're going to need. So here, 4 pi r squared for surface area of a sphere. So when I want the rate at which surface area is changing, I'm going to take the derivative of both sides of this equation with respect to time. The 2 is an exponent. It's going to come to the front to make 8 pi r. New exponent on r is going to be 1. And I wanted to take the derivative with respect to time. So far all I've done is take the derivative with respect to r. So I'm going to need to multiply by dr dt. That's where the implicit differentiation comes into this related rates problem. So the thing I want to know happens to already be isolated. The rate at which the surface area is changing with respect to time is going to equal 8 times pi times r. We said we were going to freeze at 5. And dr dt, we said from part A is 1. So the rate of change of the surface area with respect to time at the exact moment when the radius is 5, that's an equal, that says r equals 5, is equal to 40 pi. Okay, and now you have this great question, which is what are the units? You could go back to this part here, actually any part where you could jump in and replace all of those values with their values attached to units. Or you can think about this. Surface area, it's an area measurement. It has units of distance squared. And time, that dt in the denominator is time. So I know I'm going to have units, area units divided by time units. If my distances in this problem are measured in feet, then my area would be measured in feet squared. This is going to be feet squared divided by units on time are minutes. So 40 pi square feet per minute.